Now, in this video, we start studying what is probably my favorite class of Banach spaces. These are spaces that are called reflexive, and the definition is here. I'm going to say that a Banach space is reflexive if I can identify the space which is bidual. And what do I mean by that? I mean that when I look at the canonical embedding, right, which is defined this way, if you give me an element of X, I can see it as an element of the bidual, because I can see it as acting on a functional X star in the dual by the application of the functional X star to X. That clearly defines an element of X double star, which is canonically associated with X. However, not all elements of X double star in general will come in this form from an element of X. In general Banach spaces, you might have a lot more objects in X double star than just those maps. But in certain spaces, that maps turns out to be a bijection. So every element in X double star really arises from an element in X. Now, examples where that happens, well, of course, the finite dimensional spaces and the Hilbert spaces, because in that case, even the element of X star themselves can be identified with an element of X, and then an element of X star can be identified with an element of X star star for the exact same reason. So X is X star and X star is X star star. So this is the perfect situation. But beyond this perfect situation, you also have spaces that are not isomorphic to their dual, but that are still canonically isomorphic to their bidual. Perfect example, the LP spaces for P between 1 and infinity. The dual of LP is LP prime, and the dual of LP prime is LP prime prime. But what is P prime prime? It's P itself, because of the relation defining P prime as a conjugate exponent. So this class of spaces, the reflexive Banach spaces, they include a lot of our favorite spaces. It's a class that is much larger than just the class of Hilbert spaces or finite dimensional spaces, but it's not too large, as in it's a class of spaces that satisfies very good property. Now, the key property that they have, and that is very helpful in application, is that they have a lot of weakly compact set. So indeed, what we're going to prove first is that in a reflexive Banach space, any convex closed bounded set has to be weakly compact. Right, and that will be a consequence essentially of the Banach-Alaoglu theorem that gives us weak star compactness, and the fact that in the reflexive Banach space, the weak star and the weak topology will coincide. So we'll get a lot of weak compactness when we are in a reflexive Banach space. And the key theorem that we will prove in this video is theorem 9.3. It tells us that this is actually an if and only if. So if you're in a reflexive space, you know your space is reflexive because, for instance, you know, like in the LP case, how to compute the dual, then the bidual, then you can deduce that your unit ball is weakly compact. But in the other direction, if your unit ball is weakly compact, then your space has to be reflexive. So this is quite a beautiful theorem, in my opinion. It takes something that is, in a sense, purely topological, and it gives me something that looks like it's purely algebraic, although of course it's not, because the dual does contain topological information. And really, the theorem is helpful in both directions. In some cases, you know that your space is reflexive and you want to prove existence of certain things. You want to extract converging subsequences to make approximation processes converge to a solution, to create a solution of equations or prove the existence of a projection. And you can do that by exploiting the weak compactness of the unit ball, or more generally speaking, the weak compactness of closed convex bounded sets. But in the other direction, having this some more purely topological characterization allow you to show that reflexivity is invariant under various operations. We'll see that in the corollaries to the theorem. We'll see that reflexivity goes through the dual, and it goes through closed subspaces, and it goes through isomorphisms. So this then is very helpful in turn to prove that a given space is reflexive, because you see it as a combination of these operations, taking dual, taking subspaces, going through isomorphisms. And then once you know that the space you care about is reflexive, then you can exploit the weak compactness of a lot of sets. So our goal is to prove the theorem, derive the corollaries, but in the process of proving the theorem, we'll prove two lemmas that are very interesting in their own right. There's a weak star version of the Banach theorem, and there's a lemma by Goldstein that tells us that the image of the unit ball of X in B of X double star in general, without assuming anything like reflexivity, has to be still very large. It may not be everything, but at the very least has to be weakly dense. Now we'll get to this lemma in a minute as part of our proof of the theorem 9.3, but the first thing we will do is prove proposition 9.2. So show that reflexive spaces are good spaces, so spaces in which we have a nice sufficient condition to test for weak compactness, namely convexity, closedness, and boundedness. So that's really the best analog we can hope for in an infinite Banach space from the result that we have in finite dimension that every closed bounded set is compact. Okay, let's start with the proof of proposition 9.2. Now, X being reflexive tells me that when I look at the ball, the unit ball of X, I can see it as the unit ball of X double star because X and X double star can be identified, and I can use the weak star topology on this dual, and this will be the same thing as the weak topology, because testing on X or X double star is the exact same thing because X and X double star can be identified. So I have this identification of the weak star and the weak topology on the unit ball of X by reflexivity, just by definition of what these topologies are. But in the meantime, by Banach-Alaoglu theorem, I have that the unit ball is weak star compact. But if weak and weak star are the same thing on the unit ball of X, I get that the unit ball of X is weakly compact. Okay, so I have a weakly compact unit ball. Now, if I scale it, it would still remain compact. You can do the exact same covering argument, just scaling every object you use. So this means that for every R, the set RBX, which is really the ball of the closed ball of radius R, is weakly compact. Right? It's just a different notation for saying that endowed with the weak topology, it is compact. Now, I have a set K that happens to be bounded. So being bounded means that there exists an R such that K is included in RBX, and RBX is weakly compact. So all I need to show to prove proposition 9.2 is that K is weakly closed. But that's not the information that I have. The information that I have as an assumption is that K is closed. But that's almost good enough. All I need is convexity, and then Mazur theorem guarantees the weak closedness from the strong closedness. So since K is closed and convex, K is weakly closed for the weak topology by Mazur theorem. Okay, now you have a set that is weakly closed inside a set that is weakly compact. So for the appropriate topology, you have a closed set included in a compact set. It has to be compact for that topology. So therefore, K itself is weakly compact since R times Bx is weakly compact. Right? And that concludes the proof of this proposition 9.2. Fundamentally, reflexivity plus Banach-Alaoglu theorem gives us that the unit ball is weakly compact, and then combined with Mazur theorem, that gives us that any convex closed bounded set is weakly compact. So as part of our proof of proposition 9.2, we've proven one direction of theorem 9.3. We've proven that if X is reflexive, then the unit ball is weakly compact. Now we're going to work our way to proving the other direction. And to prove the other direction, we're going to need these two lemmas. So let's first prove lemma 9.4. So lemma 9.4 can be seen as a weak star version of Banach. What it tells us is that if you have a weak star closed and convex set and a point not in that set, then you can strictly separate these two sets. Well, that sounds exactly like Banach, but the subtlety is that you're not separating using a hyperplane defined by an element of the dual of X star, which will be X double star. You separate using an element of X, right? Testing on an element of X here rather than an element of x double star. So we're going to prove that. We're going to use the Banach theorem, which a priori would give us an element in x double star doing this job, and then we'll find that this element of x double star actually is an element of x. Okay, so let's prove lemma 9.4. I have an element x naught star, which is not in my set B, so it's in the complement of B. Now the complement of B has to be weak star open, because B itself is weak star close. So that means that I have a weak star neighborhood around x naught star within the complement of B. That is to say, there exists an epsilon, and there exists an n in n, and there exists element x1 till xn in capital X, such that the neighborhood V, which is in the notation of neighborhoods for the weak star topology, V epsilon x naught star x1 till xn, lives entirely within B complement. So that V is open and convex, and the B itself is convex. Okay, so by the standard Banach theorem, I can separate V from B by an element using an hyperplane compared to x star, so using an element of x double star. So there exists an element x naught double star in capital X double star, and there exists an alpha in R such that x naught double star tested on x naught star is smaller than alpha, and that is smaller than x naught double star y star. That's not just x naught star, it's x star, and that's y star, and that's for every x star in V and for every y star in B. Right? I'm separating V from B as subsets of x star, strictly separating this open convex set from a convex set. So what I need to show to get the result I want is that x naught double star that I got by standard Banach is actually an element of x. It can be identified with an element of x. Now, in order to do that, so I want to recall that if I have that the kernel of the xj, or the intersection of those kernel from j equal 1 to n, is included in the kernel of x naught double star, we've seen an argument previously that guarantees that this means that x naught double star is actually in the span of the xj's, and therefore has to be an element of x, or can be identified as an element of x. So what we need to show really is this intersection of kernel. So, okay, so let's do that. Let's take an element x star in the intersection of the kernel of the xj's and see what this gives. So if I have an element like that, and I give myself a bit of room, so I give myself a scalar number t, I'm going to have that for every j. Okay, what happens when I test x naught star plus tx star on an xj? Okay, well, x star is in the kernel of the xj, so all of that is just x naught star xj, and x naught star xj has to be smaller than epsilon. So, okay, so that means that for every t in R, x naught star plus tx star has to belong to V. Okay, but if that happens, then because I've separated V from B, I get that x naught double star, x naught star plus tx star will have to be smaller than alpha for every t in R. And that's not possible unless x star comma x naught double star is 0. Because if it were not 0, it can be positive or negative by taking t t positive or negative large enough, you would contradict this inequality. So this can only happen if x star tested on x naught double star is 0, and that is exactly saying, of course, that x star is in the kernel of x naught double star. And then the argument we have seen previously guarantees that this can only happen if x naught double star is in x, in fact, is in the span of the xj. Okay, so now that we have lemma 9.4, the weak star version of Banach theorem, we can prove lemma 9.5. So the theorem of Goldstein that tells us that the image of the unit ball of x seen inside the unit ball of x double star has to be weakly dense. And that's going to be a very helpful result as we go forward. So here's how you prove it. By contradiction, you assume it's not true. So you assume that the unit ball of x double star, if you take away from it the image of b of x and close that in the weak topology, you assume that this is non-empty. Okay, but if it's non-empty, if you subtract less, then it's going to be even less empty. So if I subtract the weak star closure of IBX, then it's non-empty. And so I can pick an element, x naught double star, in here. But now what do I have? I have an element that is not in this weak star closed and convex set. So I can apply lemma 9.4, and lemma 9.4 will tell me that I can find an element in x star, let's call it x naught star. So I apply lemma 9.4 not in x looking at x double star, but I apply it in x star looking at x double star. And then there exists an x naught star in x star, and there exists an alpha in R, for which I have that x naught star is smaller than alpha and is smaller than x naught star, x naught double star. So really I should write ix here, and that's for every x in the unit ball of x. Right? I'm separating the image of the unit ball, or in fact it's weak star closure, so I could have a lot more than just this kind of elements. I could have weak star limits thereof, for instance, and I separate that from the single point x naught double star. But this will lead to a contradiction, because if I have that, then I have that for every x in x, x acted upon by x naught star is smaller than alpha, that is smaller than the norm of x naught star times the norm of x naught double star, right? But x naught double star is an element, well, not just of x double star, but of the unit ball of x double star. So it has norm at least one, at most one. So this is certainly smaller than x naught star. But now you could take a supremum over all x in x, over all x in the unit ball of x of this. And sure, this inequality would become a large inequality, and that would be smaller than x naught star. But that's still a contradiction, because this is equal to the norm of x naught star, and the norm of x naught star cannot be strictly smaller than itself. So that's how you get a contradiction, and that's it. That's the proof of Goldstein lemma. So the image of the unit ball of a Banach space inside the unit ball of its bidual has to be weakly dense. Okay, now that we've proven Goldstein lemma, proving theorem 9.3 is pretty much straightforward. One direction we've already proven. We've already shown that when x is reflexive, essentially by Banach-Alaoglu theorem, the unit ball of x endowed with the weak topology is compact, because it's the same as the unit ball of x endowed with the weak star topology, which is compact by Banach-Alaoglu. Now, in the other direction, if bx t omega t weak is compact, right? Now that tells us that the image of this by a continuous map will have to be compact. So I of bx, seen as a subset of bx double star, also endowed with the weak topology, has to be compact. Okay, but it is also dense, is weakly dense in bx double star by Goldstein lemma 9.5 that was. So you have something that is weakly dense and weakly compact, so in particular weakly closed. So this tells you that it has to be equal to b of x double star. It's equal to its weak closure, and its weak closure is bx double star. But now the map I is linear, so you could scale all of that. And so for every r positive, I of r bx is r of bx double star. But now that means that any element in x double star will be the image of an element in x through the map I, and therefore the map I is surjective. It's obviously injective, so it is a bijection. And that completes the proof of our key theorem. So it's really a consequence of Banach-Alaoglu in one direction and Goldstein theorem in the other direction. Goldstein itself being, if you want, a consequence of Banach, but really interpreted in the appropriate way using the weak and the weak star topology. Okay, now that we have this, in a sense, purely topological characterization of reflexivity through theorem 9.3, we'll see that this guarantees the stability of the reflexivity conditions in many ways. So first up is the corollary 9.6 that tells us that a Banach space is reflexive if and only if its dual is reflexive. So how do we prove that? Well, first assume X is reflexive. Okay, so what does that give us? That gives us that the unit ball of the dual with the weak topology is the same as the unit ball of the dual with the weak star topology. Weak and weak star topology can be identified when X can be identified with its bi-dual, so almost by definition. And now by Banach-Alaoglu, this implies that the unit ball of the dual with its weak topology is compact. Okay, but then theorem 9.3 exactly guarantees that this implies that X star is reflexive. Now in the other direction, let us assume that X star is reflexive. So if X star is reflexive, then by the first step of the proof, I have that X double star is reflexive. So X star reflexive implies X double star reflexive. And by the theorem, I have that this implies that the unit ball of X double star with its weak topology is compact. Okay, but now if I look at the image of the unit ball of X inside Bx double star, now this is a closed and convex set. So by Mazur theorem, it's weakly closed. Weakly closed inside Bx double star. Now, if you're weakly closed inside a weak compact set, then you're weakly compact. So you have that I of Bx with the weak topology on X double star is compact. Okay, but remember that X star is reflexive. So this IBXT omega is equal to IBX with T weak star. Okay, because that's the same thing. So this is weak star compact, but the weak star topology on X double star is really the weak topology on X, right? Because you're testing, sorry, the weak star topology on X double star restricted to the image of the unit ball of X is really the weak topology on the unit ball of X. So this is identifiable to the ball of X with its weak topology. And this has to be compact, but this then, again by theorem 9.3 guarantees that X itself is reflexive. Okay, so reflexivity is a self-dual property. So now that we've seen that reflexivity passes to duals, we'll see that it's also a stable undertaking subspaces or isomorphisms of Banach spaces. So let's start with subspaces. I have a reflexive Banach space X, and by the theorem 9.3, I know that its unit ball with the weak topology is compact. Now, what if I look at the unit ball of the closed subspace X not seen as a Banach space, which I can do because it's a closed subspace of a Banach space. This is going to be a subset of the unit ball of X, and it's a subset that's closed and that's convex. Right. Now, Mazur's theorem guarantees that this subset, B of X naught, is weakly closed. Okay, but if you are weakly closed inside a weakly compact set, then you have to be weakly compact. So the ball here is weakly compact. Now it's weakly compact, but it's seen, as a subset of X itself. So this is not quite guaranteeing yet that X naught is reflexive, but almost. Let's just go back to the definition of being weakly compact. So this means that we can cover it by a finite unions of neighborhoods. So B of X naught can be covered by a finite union of sets of the form V epsilon X x1 star till xn star, where X is an element of Bx naught, so it's an element of the subspace capital X naught, and it has norm at most 1, and the xj star are element of the dual of X. So that's the little caveat here, the element of the dual of X. Does that mean that the element of the dual of X naught star? Well, of course, because if X naught is a closed subspace of X, then X star is a subspace of X naught star, right? Because being in X star means that you're continuous when you test against every element of X, whereas being in X naught star only means you're continuous when you test against element of X naught. So it's much easier to be continuous in the sense of X naught star that it is to be continuous in the sense of X star, because you're testing on more things in X star than in X naught star. So really, Bx naught can be covered by a finite unions of neighborhood in the weak topology of X naught. So this is really saying that Bx naught is weakly compact in the topology of, so weakly compact in the topology of, in the duality X naught star, rather than just the duality XX star. Therefore, by the theorem, X naught is reflexive. Just covering by neighborhoods from the point of view of the topology of the weak topology of X is more demanding than covering by neighborhood in the weak topology of X naught star. Right, so that proves the first part of corollary 9.7, namely that reflexivity goes to subspaces. Now let's have a look at what happens through isomorphisms. Okay, so I have an isomorphism of Banach spaces between X naught and Y. That is to say, a continuous linear map which inverse is continuous and linear, while the open mapping theorem will guarantee its continuity as soon as I have a inverse from a linear algebraic point of view. So I have this isomorphism of Banach spaces between the Banach space X naught and the Banach space Y. And the first thing I want to show really is that this map T is a continuous map if I endow x0 and y with their respective weak topology, right? Because I want to see whether or not the unit ball of y with the weak topology is compact. So let's check that. Let's take a neighborhood from the point of view of the weak topology of y. And then let's see if its inverse image through T is a weakly open set from the point of view of the weak topology of x0. So I take a V that is of the form V epsilon T of x0 y1 star till yn star. Right, that's a neighborhood inside of y. And I can do that. An arbitrary neighborhood inside of y will be centered at a point of the form T of x0 for some x0 in capital X0 because T is an isomorphism. Now, what is the inverse image by T of such a V? Well, it is the set of all x in X such that T of x is in V. And what does that mean that T of x is in V? It means that T of x is close to T of x0 from the point of view of the yj stars. So these things are all smaller than epsilon for all j equal 1 to n. But now, because T is a linear map, it has an adjoint. It's a bounded linear map, it has an adjoint. So I can get to the adjoint and turn my testing condition to a condition on x minus x being close to x0. And what is that? Well, this is literally a weak neighborhood in the topology of x0, in the weak topology of x0. This is the weak neighborhood of size epsilon centered at x0 with the testing functional being the image by t star, which is a map from y star to x0 star of dt star y j star. Okay, so the image of a neighborhood, the inverse image of a neighborhood in the weak topology of y is a neighborhood in the weak topology of x0. That is to say that T, seen as a map from x0 with its weak topology to y with its weak topology, is continuous. But okay, if I have a continuous map between two topological spaces, it sends compact set to compact set. And so the image, so by of t omega, right, what can I say about that? Well, I can say that this is the image by t of the inverse image of by, and all of that seen with respect to the weak topology. But now the inverse image of by is weakly closed inside a weakly compact set. Is weakly compact. Well, it's compact for the weak topology, right? Because x0 is reflexive. Therefore, t minus 1 by is weakly closed. And so its image by t, which is a continuous map for the weak topology, has to be, with respect to the weak topology, weakly compact. I said it's weakly closed, but it's actually, I knew that it's weakly closed and therefore weakly compact as a weakly closed subset of a weakly compact set. And now theorem 9.3 tells me that well, y itself will have to be reflexive because its unit ball endowed with the weak topology is compact. Okay, and that concludes the proof of this corollary. The take-home message after these two corollaries is that reflexivity is a very stable property. It's stable under taking a joint, it's stable under taking closed subspaces, it's stable under taking isomorphism, and combining all of that, you could also see that it's stable under quotienting by the equivalence relationships deriving from a closed subspace. So it's a very stable property, and it's a very useful property in the sense that it gives us plenty of compact sets. All of the closed convex bounded set will be compact. Now we'll see in the rest of this chapter how helpful this is.